Neutrinos 1930 to 1962. For the third strand in the story, we return again to the year 1930. A problem had arisen in the study of nuclear beta decay. In beta decay, a radioactive nucleus A is transformed into a slightly lighter nucleus B with the emission of an electron. A goes to B plus electron. Conservation of charge requires that B carry one more unit of positive charge than A. We now realize that the underlying process here is the conversion of a neutron in A into a proton in B. But remember that in 1930, the neutron had not yet been discovered. Thus, the daughter nucleus B lies one position further along on the periodic table. There are many examples of beta decay. Potassium goes to calcium, copper goes to zinc, tritium goes to helium, and so on. The upper number is the atomic weight, the number of neutrons plus protons, and the lower number is the atomic number, the number of protons. Now, it is characteristic of two-body decays such as expression 1.6 that the outgoing energies are kinematically determined in the center of mass frame. Specifically, if the parent nucleus A is at rest so that B and E come out back to back with equal and opposite momenta, then conservation of energy dictates that the electron energy is E equal ma square minus mb square plus me square divided by 2ma whole multiplied by c square. The derivation of this result will be explained in chapter 3. For now, the point to notice is that E is fixed once the three masses are specified. But when the experiments are done, it is found that the emitted electrons vary considerably in energy. Equation 1.7 only determines the maximum electron energy for a particular beta decay process. See figure 1.6. Figure 1.6. The beta decay spectrum of tritium. Tritium to helium. Source G.M. Lewis, Neutrinos, London, Wykeham, 1970, page number 30. This was a most disturbing result. Niels Bohr, not for the first time, was ready to abandon the law of conservation of energy. It is interesting to note that Bohr was an outspoken critic of Einstein's light quantum prior to 1924, that he discouraged Dirac's work on the relativistic electron theory, telling him incorrectly that Klein and Gordon had already succeeded, that he opposed Pauli's introduction of the neutrino, that he ridiculed Yukawa's theory of the meson, and that he disparaged Feynman's approach to quantum electrodynamics. Fortunately, Pauli took a more sober view, suggesting that another particle was emitted along with the electron, a silent accomplice that carries off the missing energy. It had to be electrically neutral to conserve charge, and also, of course, to explain why it left no track. Pauli proposed to call it the neutron. The whole idea was greeted with some skepticism, and in 1932, Chadwick preempted the name. But in the following year, Fermi presented a theory of beta decay that incorporated Pauli's particle and proved so brilliantly successful that Pauli's suggestion had to be taken seriously. From the fact that the observed electron energies range up to the value given in equation 1.7, it follows that the new particle is extremely light as far as we know. Its mass is in fact 0. Fermi called it the neutrino. For reasons you'll see in a moment, we now call it the antineutrino. In modern terminology, then the fundamental beta decay process is neutron goes to proton plus electron plus antineutrino. Now you may have noticed something peculiar about Powell's picture of the disintegrating pion, figure 1.4. The muon emerges at about 90 degrees with respect to the original pion direction. That's not the result of a collision, by the way. Collisions with atoms in the emulsion account for the dither in the tracks, but they cannot produce an abrupt left turn. What that kink indicates is that some other particle was produced in the decay of the pion, a particle that left no footprints in the emulsion and hence must have been electrically neutral. It was natural, or at any rate economical, to suppose that this was again Pauli's neutrino. Pion goes to muon plus neutrino. A few months after their first paper, Powell's group published an even more striking picture, in which the subsequent decay of the muon is also visible. Figure 1.7. Here, a pion decays into a muon plus a neutrino. The muon subsequently decays into an electron and two neutrinos, reprinted by permission from C.F. Powell, P.H. Fowler and D.H. Perkins. The Study of Elementary Particles by the Photographic Method, New York, Pergamon, 1959, first published in Nature, 1949. Now, muon decays had been studied for many years, and it was well established that the charged secondary is an electron. From the figure, there is clearly a neutral product as well, and you might guess that it is again a neutrino. However, this time it is two neutrinos. Muon goes to electron plus two neutrino. How do you know there are two of them? Same way as before, we repeat the experiment over and over, each time measuring the energy of the electron. If it always comes out the same, we know there are just two particles in the final state. But if it varies, then there must be at least three. By 1949, it was clear that the electron energy in muon decay is not fixed, and the emission of two neutrinos was the accepted explanation. Here and in the original beta decay problem, conservation of angular momentum also requires a third outgoing particle. Quite independently of energy conservation, but the spin assignments were not so clear in the early days, and for most people, energy conservation was the compelling argument. In the interest of simplicity, I will keep angular momentum out of the story until chapter 4. By contrast, the muon energy in pion decay is perfectly constant within experimental uncertainties, confirming that this is a genuine two-body decay. By 1950, then, there was compelling theoretical evidence for the existence of neutrinos, but there was still no direct experimental verification. A skeptic might have argued that the neutrino was nothing but a bookkeeping device, a purely hypothetical particle whose only function was to rescue the conservation laws. It left no tracks, it didn't decay. In fact, no one had ever seen a neutrino do anything. The reason for this is that neutrinos interact extraordinarily weakly with matter. A neutrino of moderate energy could easily penetrate 1,000 light years of lead. That's a comforting realization when you learn that hundreds of billions of neutrinos pass through every square inch of your body per second, night and day. Coming from the sun, they hit you from below at night, having passed right through the earth. To have a chance of detecting one, you need an extremely intense source. The decisive experiments were conducted at the Savannah River Nuclear Reactor in South Carolina in the mid-50s. Here, Cohen and Reines set up a large tank of water and watched for the inverse beta decay reaction. Antineutrino plus proton goes to neutron plus positron. At their detector, the antineutrino flux was calculated to be 5 × 10⁻13 particles per square centimeter per second. But even at this fantastic intensity, they could only hope for 2 or 3 events every hour. On the other hand, they developed an ingenious method for identifying the outgoing positron. Their results provided unambiguous confirmation of the neutrino's existence. As I mentioned earlier, the particle produced in ordinary beta decay is actually an antineutrino, not a neutrino. Of course, since they are electrically neutral, you might ask, and many people did, whether there is any distinction between a neutrino and an antineutrino. The neutral pion, as we shall see, is its own antiparticle. So too is the photon. On the hand, the antineutron is definitely not the same as a neutron. So we are left in a bit of a quandary. Is the neutrino the same as the antineutrino? And if not, what property distinguishes them? In the late 50s, Davis and Hammer put this question to an experimental test. From the positive results of Cohen and Reines, we know that the crossed reaction neutrino plus neutron goes to proton plus electron must also occur and at about the same rate. Davis looked for the analogous reaction using antineutrinos. Antineutrino plus neutron goes to proton plus electron. He found that this reaction does not occur and thus established that the neutrino and antineutrino are distinct particles. Davy's result was not unexpected. In fact, back in 1953, Konopensky and Mahmoud had introduced a beautifully simple rule for determining which reactions, such as 1.12, will work and which, like 1.13, will not. In fact, they assigned a lepton number L equal plus 1 to the electron, the muon and the neutrino, and L equal minus 1 to the positron, the positive muon and the antineutrino. All other particles are given a lepton number of 0. Konopensky and Mahmoud, reference 12, did not use this terminology and they got the muon assignments wrong. But never mind, the essential idea was there. They then proposed the law of conservation of lepton number, analogous to the law of conservation of charge. In any physical process, the sum of the lepton numbers before must equal the sum of the lepton numbers after. Thus, the Cohen-Rains reaction 1.11 is allowed, L equal minus 1 before and after, but the Davis reaction 1.13 is forbidden. On the left, L equal minus 1, on the right, L equal plus 1. It was in anticipation of this rule that I call the beta decay particle in expression 1.8 an antineutrino. In view of the conservation of lepton number, the charged pion decays 1.9 should actually be written pion goes to muon plus antineutrino, antipion goes to antimuon plus neutrino, and the muon decays are really muon goes to electron plus neutrino plus antineutrino, antimuon goes to positron plus neutrino plus antineutrino. What property distinguishes the neutrino from the antineutrino then? The cleanest answer is lepton number. It's plus 1 for the neutrino and minus 1 for the antineutrino. These numbers are experimentally determinable, just as electric charge is, by watching how the particle in question interacts with others. As we shall see, they also differ in their helicity. The neutrino is left-handed, whereas the antineutrino is right-handed. But this is a technical matter best saved for later. There is a final twist to the neutrino story. Experimentally, the decay of a muon into an electron plus a photon is never observed. Muon does not goes to electron plus photon, and yet this process is consistent with conservation of charge and conservation of lepton number. Now there is a very reliable rule of thumb in particle physics generally attributed to Richard Feynman, which says that whatever is not expressly forbidden is mandatory. The absence of muon goes to electron plus photon suggests a law of conservation of mu-ness. But then how are we to explain the observed decays muon goes to electron plus neutrino plus antineutrino? The answer occurred to a number of people in the late 50s and early 60s. Suppose there are two different kinds of neutrino, one associated with the electron neutrino, and one with the muon neutrino. If we assign a muon number L muon equal +1 to muon and muon neutrino, and L muon equal -1 to anti-muon and muon antineutrino, and at the same time an electron number Le equal +1 to electron and electron neutrino, and Le equal -1 to positron and electron antineutrino, and refine the conservation of lepton number into two separate laws: conservation of electron number and conservation of muon number. We can then account for all the allowed and forbidden processes. Neutron beta decay becomes neutron goes to proton plus electron antineutrino. The pion decays are pion goes to muon plus muon antineutrino. Antipion goes to antimuon plus muon neutrino, and the muon decays take the form muon goes to electron plus electron antineutrino plus muon neutrino. Antimuon goes to positron plus electron neutrino plus muon antineutrino. I said earlier that when pion decay was first analyzed, it was natural and economical to assume that the outgoing neutral particle was the same as in beta decay. And that's quite true. It was natural and it was economical, but it was wrong. The first experimental test of the two neutrino hypotheses and the separate conservation of electron and muon number was conducted at Brookhaven in 1962. Using about 10 to the power 14 antineutrinos from pion decay, Leatherman, Schwarz, Steinberger and their collaborators identified 29 instances of the expected reaction. Muon antineutrino plus proton goes to antimuon plus neutron, and no cases of the forbidden process. Muon antineutrino plus proton goes to positron plus neutron. With only one kind of neutrino, the second reaction would be just as common as the first. Incidentally, the experiment presented truly monumental shielding problems. Steel from a dismantled warship was stacked up 44 feet thick to make sure that nothing except neutrinos got through to the target. By 1962, then, the lepton family had grown to 8. The electron, the muon, their respective neutrinos and the corresponding antiparticles. Table 1.1. Table 1.1. The lepton family, 1962 to 1976. Leptons. Electron. Lepton number 1, electron number 1, muon number 0. Electron neutrino, lepton number 1, electron number 1, muon number 0. Muon, lepton number 1, electron number 0, muon number 1. Muon neutrino, lepton number 1, electron number 0, muon number 1. Antileptons, positron, lepton number -1, electron number -1, muon number 0. Electron antineutrino, lepton number -1, electron number -1, muon number 0. Antimuon, lepton number -1, electron number 0, muon number -1. Muon antineutrino, lepton number -1, electron number 0, muon number -1. The leptons are characterized by the fact that they do not participate in strong interactions. For the next 14 years, things were pretty quiet as far as the leptons go. So this is a good place to pause and let the strongly interacting particles, the mesons and the baryons, known collectively as the hadrons, catch up.